Hello students, so continuing our lectures on silicon photonics. In our previous lecture, we have that was lecture number we will to lecture number 248. We have discussed about why is it necessary to couple silicon photonics with photonic crystal cavities. It can be a micro or nano cavities for a better photonic device. Now we will go into deep in this lecture. So what we have discussed about these photonic crystal cavities, they have very high Q value. So what is actually Q value? Q is actually the ratio between the central frequency with which the information or the light is being passed divided by the bandwidth. So if you have a high Q, it implies that for a fixed frequency, we have a high Q, then implies that the bandwidth is low, and this bandwidth is associated with the noise or the rate of energy loss. So a high Q indicates that uh, the rate of energy loss is less, and also the lower noise. Because we are having a high Q, it indicates that the bandwidth is narrow, and we get these high Q values in the case of photonic crystals. Now photonic crystal is, on the other hand, if you look into the structure of photonic crystal, is actually a crystal made up of materials of or periodic arrangements of different refractive indices. So these are the materials, and each one of them will have a so if this is so the base material might be having a refractive index of its own, one, and these materials will be having a refractive index different from the base material. So light is able to pass through these photonic crystals, and this undergoes what happens in the case of XRD diffraction through the atoms. It passes through. Similarly, when light passes through this photonic crystal, it undergoes scattering and whatever other optical phenomena. Now our main role is to find uh, a material, find a system with high Q. This is our main objective. Now the problem with these devices is that the base material is usually the silicon dioxide, SiO2, and due to and getting a high Q value, and this is called the cladding, and achieving a high Q value in the presence of a cladding is sometimes difficult. So what has been opted a mechanism of something called uh, wood gap confined cavity. or you can also call it as the uh, width modulated line defect cavity. So what is actually this line defect cavity? Now it is an arrangement by which we are, suppose we have an array of refractive index uh, material. This is the array for the Fourier. Suppose we are dealing with a two-dimensional photonic crystal. We have array of refractive materials and irregular pattern. Now suddenly in some area, if you find that the width has some changes, that means what I mean is that means for a certain area D, for example, you see that this width, let's call it as W1, is much less than this width W2. So we have created a width modulation, and this is called the line defect. It is analogous to the line defect that we obtain in case of crystals, that is edge defect and screw defect. Now this line defect helps in propagation of waves. Now what happens is that due to uh, there is a dispersion. Dispersion means change of wavelength, or scattering, or the wave getting scattered with respect to its wavelength or frequency, whatever we may call it. So what we observe is that by increasing the width of the line, we actually can shift the mode. So if we
स्कूल का नया साल शुरू हुआ। क्या क्या पढ़े ये सवाल शुरू हुआ। हिस्ट्री साइंस।
so if we plot between the normalized frequency periodicity divided by the wavelength, and if we plot the wave vector a by 2 pi here, then what we obtain is we obtain a plot like this. This is for say width W1, and if we increase the width, there is a slight change in the dispersion spectrum. So there is a shifting down of mode. So we are shifting it towards a lower frequency by creating the by increasing the width. So W2 is greater than W1. We have increased the width, but we have lowered the frequency. Now the frequency component close to the mode gap, that is k wave vector in case of Brillouin zone. This will be localized. This will get localized. That means if we shift only hole only in a certain place, we get a photonic crystal waveguide. By shifting the hole, by which we mean that if there are two photonic crystals, the space in between them. So by shifting this, we are actually allowing the move waveguide to flow through the crystal. So this actually solves the problem of having or achieving a higher Q value due to the presence of this cladding. Because localized mode wave vector of a width modulated line defect is very well. So if you look at this is the line of the light line of the SiO2. So even if it is you are having an SiO2 cladding layer, it is lower than the light line of the cladding. So if there are small vertical radiation loss occurring, and we can expect a high Q value even if we are having a cladding.